Truth. In this video, we will look at a differential equation with some population growth. So let's look at this problem. Suppose you have a population of a species that initially has 288 members and has a growth rate that is linear with its population. So the goal here is for us to somehow understand the connection between these various quantities and then use it to write a differential equation. If a function, find a function that models its population with respect to time t. So the first part here, the answer to this question is a function. Okay? So I know this is kind of weird that we answer a problem by finding a function, but that's what solving a differential equation is asking for. Instead of solving for a variable or a constant or some number, we're solving for a particular function. And then the second part of the problem, if p of 8 is equal to 800, determine when the population will reach 1500. So let's do the first part first. And I'm going to define a few things. We're going to say that P of t represents the population at time t. The population at time t. And then I'm going to define dp dt. And now this definition is not arbitrary. It is very much based on what we know about calculus. dp dt is the derivative or the rate of change of the population. So using this information here, the population is linear to its growth rate. So growth rate here is another way of saying dp dt. So dp dt and p are linear. So we can express it this way. dp dt is equal to k times p, where k is also some constant. And what that constant is, we will figure out a little bit later. All right, so this function seems relatively simple. This equation, I should say, seems relatively simple. And now we just have to, apply what we know about differential equation. We're going to separate the variables. So I'm going to divide both sides by p. And I'm going to multiply both sides by dt. So I get k dt is equal to dp over p. Let's then now take the antiderivative of both sides, or differentiate both sides. And let's see what we get. Well, let's see. The antiderivative of this is really 1 over p. So I get the natural log of the absolute value of p plus some constant. I guess I'll call this c1 is equal to, now the antiderivative of a constant with respect to t is just kt plus some other constant. I'm going to merge those two constants together into a big constant. So actually, let's do that. Is going to be equal to kt. Now c2 minus c1, whatever that is, it's some other constant. We'll deal with that later. And I'm going to solve for p. So keep in mind this is the natural log of something, and I want to get p out of there. So we're going to convert it to exponential form. Okay, so I'll write some note here. We're going to convert to e exponential form. So this natural log, remember, is log base e. So this tells me that p is equal to e to the kt plus c. And I'm just going to add a little bit more of a wrinkle to this to simplify this equation further. Remember that properties of exponents, whenever you're adding two exponents, what you're really doing is multiplying by the same base. Okay, so e to the kt plus c is the same thing as e to the kt times e to the c. Now e is a constant, c is a constant, so this here is also a constant as well. And so my final and simplest version that I can write for this is that p of t is equal to I'm just going to move this in the front, the constant, e to the kt. So there you have it. That finishes the problem for the first part. We've solved this, and this is the general solution. In the next video, we will deal with what I call the more specific, or the specific solution. So we haven't actually used any of the other information yet. P of 8 is equal to 800. We'll deal with that a little bit later. As always, ask for help if you need it. Thank you for watching, and have a wonderful day.